Okay, now welcome back. We will continue a few more points regarding the discussion or the discussion on the introduction towards the design of isolated footings. Some points in addition to what you have studied in your geotechnical engineering. We have basically some IS codes. One is IS 1080, another is IS 1904. These two codes are for the code of practice for design and construction of shallow footings or shallow foundations. Okay, and 1904 is the general requirements. So if you go through this IS 1080, uh, some points are written regarding the bearing capacity. Okay, then cement concrete foundation should be designed based on IS 456. These things are written there. Then types of foundation IS 1904 has specified like shallow, deep foundation and special foundations. Shallow foundation types are various like spread pad, which is the one we are going to study in our design of concrete structures that are in this subject. Then we have strip, raft, and ring and shell foundation. Strip and raft they carry more than one column. Ring and shell foundation are used in special conditions where we cannot expect that much of bearing capacity. Deep foundation, piling, caissons, wells, etc. All these things are covered or described by this IS 1904. Then, as regards to bearing capacity, calculation of that, which you must have studied in your geotechnical engineering, it should be done as per IS 6403, IS 6403, and also as regards to the settlement of this particular soil. So, due to that settlement of foundation, uh, they have two types. One is uniform settlement, another is differential settlements. So these points are also discussed there. Now, coming on to the settlement part, shear strength part of soil, etc. The last class I told you that whenever we decide a value of bearing capacity, it is based on all these considerations. So in classroom problems, whenever you get a bearing capacity, whether it is safe bearing capacity or ultimate bearing capacity, safe and ultimate means divided by factor of safety will be the safe bearing capacity. Factor of safety ranges from 1.5 to 3 based on various conditions. So you have ultimate bearing capacity or safe bearing capacity. In this value, whatever value we arrive at is encapsulating the concept of shear failure as well as settlement. Now, type of isolated foundation, what are the loading on the isolated footings? The most common type is axial load P along with a moment M. And in real practice, you can have this moment M in two directions, X and Y directions, which is a biaxial moment. We have already studied the design of biaxial columns where an interaction curve, etc., is required for designing of that columns. And in case of a footing, when it is biaxial bending, the calculations are quite complicated. The most simple one is a footing with only vertical, concentric vertical loading acting, P acting. Next is P with M. Next is P with M and M. So P, PM, P, MM. Out of this, P only is very easy to design, but PM, PMM, etc. are laborious to design. Then there can be footings where only P acting, where only moment acting. These conditions can also come. In addition to that, the P may be inclined. Okay, so that condition also will be there because in a typical building you can have vertical as well as horizontal forces. So it's a resultant when you do the structural analysis. The vertical force plus horizontal force, you may consider it as an inclined force P. So in that case, the P, even though it is acting at the central central line of the column, due to that slant of that force P, it will be hitting the ground below the foundation with a what is called an eccentricity, not at the center line. So whenever it is not at the center line, we call it as eccentricity. Similarly, another case of eccentricity with the vertical force, when the force is not exactly on the center line of the column, that also can happen. And in that case, we have an eccentricity E. So P only, but with E. That means P plus a moment M, value of which is given by P into E. So whatever you see on the left hand side is similar one when P is with an eccentricity. Okay, so in that case, this M will become this M. In that case, will become P into E. That's all. That is only. So that is a case. So these are the various cases of loading in a typical uh, isolated footing. But the most easier one is uh, the one footing with P only, with M equal to 0. It is very easy to do the design calculations in a vertical load only footing. But that is very rare in the real field, or in the case of a typical building in the field. You will never get a footing having only P. And in addition to P, you need to add delta P also. Delta P is of course you are getting from the structural design, the weight, dead weight and live load of the building as a whole, then analyzed using a proper method. You will get this P due to dead and live load of the structure. In addition to that, delta P also will be there. That delta P is a small value of P. That's why delta P is written. It's not incremental P as usually we use in mathematics. It is not an incremental P. It is another small P, weight of the footing and weight of the backfill. Delta P represent weight of footing because this is a footing. So this footing will have some self weight, and you can see the backfill also here. That also will have some self weight. So that is delta P. Okay. So three types of loading basically whenever we are in a single plane, the P, delta P, and M. And when we see the pressure exerted on the soil by the footing, we can see delta P is a direct force, so the pressure will be PIA. So delta P by A. I have drawn a parallel set of parallel lines to represent because delta P by A is constant throughout the width of the footing. Suppose A is the area of the footing. If you see in the plan, you can see length and breadth, or breadth, length, rectangular if it is breadth and length, square if it is breadth and breadth. Multiply these two quantities, you are going to get the area of the footing. So that delta P by A is the pressure exerted by delta P on the soil. So that diagram I have represented there, delta P by A, uniform pressure. Then next one, due to the capital P, that is also a direct vertical loading, so it is also uniform P by A. That is a uniform pressure throughout the width and breadth of the footing P by A. In addition to that, you have that M. So the pressure due to M is M by Z, that you know. Where we have studied that bending theory also. M by Z. Z is the modulus of the section of the footing. If it is B by D, then you know how to calculate BD square by 6. You know to calculate that. So that is Z. So M by Z is the pressure. This is not uniform. This is linearly varying, M by Z. And in that, you can see the right hand side, if the moment is clockwise, when we see this slide, in this slide, the moment is clockwise, moment can be anti-clockwise also. So whenever you have a clockwise moment acting, then the right side triangle, that is this one, that is this triangle. This triangle is under downward pressure, or that portion, the footing will be exerting a downward pressure to the footing, sorry, soil. But the another triangle, this one, that is the pressure from the footing is acting upwards, because that footing is trying to get tilted. So due to right side tilting or clockwise tilting, we can imagine that. So whenever the footing is tilting clockwise or tend to tilt, not tilting actually, it will try to tilt. In that case, you know that that footing will be this portion. This portion of the footing will be exerting downward pressure, and this portion of footing will be getting lifted up. So upward pressure. Okay. So this is the three types. Of, these are the three types of pressure: downward or upward acting on a soil from the footing. So you can add it algebraically, because principle of superposition is valid. So effect of delta P, capital P, and M can be added. So when you try to add that one by one, you will get this as a net diagram. Okay. So that blue portion will get cancelled actually, because previously, or if you look down, you can see that this portion, this blue portion, it is upward, this portion is downward. So when you combine it, this will get cancelled. There is no pressure. So ultimately, a trapezoid of pressure you will get, and the pressure due to applied loadings are algebraically added, resulting in a trapezoidal pressure exerted by the footing on the soil. So that values, right hand side, it will be okay. I have drawn the trapezoidal variation of soil, of the pressure from footing onto the soil. Right hand side, it is delta P by A plus delta P by A plus M by Z, because everything is acting downwards. But on the left hand side of the uh, that is at this location, delta P by A both are acting downwards, but M by Z is acting upwards, so that is minus M by Z. So this is the trapezoidal pressure exerted by the footing onto the soil, and in reaction, the soil will be supporting or resisting this pressure, and that resisted pressure is, we call it as QU, soil pressure, or we call it as bearing capacity also, which you have studied in your geotechnical engineering. So generally the term given is QU. So a QU is mobilized inside the soil, so soil will not get compressed. Soil instead will be keeping the footing afloat by exerting this pressure QU max or min. QU max. So these two should be matching. These two should be matching, or this quantity should not exceed QU minimum. This quantity should not exceed QU max for the soil to support the foundation. This QU max is known as ultimate bearing capacity, or at least it should not exceed ultimate bearing capacity. Suppose the soil is having an ultimate bearing capacity of 500 kilonewton per square meter, then the value calculated delta P, this quantity, it should be less than, the value calculated should be less than that 500 kilos. That 500 I have told as an example of, it's called an ultimate bearing capacity. You know how to calculate ultimate bearing capacity from geotechnical engineering classes. We have a concept of ultimate bearing capacity as well as its factored value divided by 1.5 divided by 2, etc., which is called the safe bearing capacity. So these are the type of soil pressure distribution beneath the foundation, and how the soil is supporting. Or this is the pressure exerted by the foundation, and the bottom trapezoidal distribution is the pressure provided or support provided by the soil to support the foundation. But whenever you have only P, which is a very fictitious case, P and delta P, then the figure will be quite simple because both are uniform, acting downwards uniform eccentrically, concentrically. So you can see a uniform pressure exerted by the footing onto the soil. That is, this one is uniform, given by delta P plus P by A. Okay, and naturally in return, soil will be exerting a uniform pressure. Okay, that is QU max should be less than ultimate bearing capacity of soil. So in our classroom problems or your examination, we will be doing this type of questions. Okay, question with M, as you have seen, you have a trapezoidal variation of this QU. So that calculations are quite complicated. So I think you should expect only a vertically loaded or the footing design without any movement. Okay, so that is the introduction. Let us try to do two problems based on your syllabus. Two problems are there. Two types of problems are there. Let us try to do that. So we will be doing all the problems with only P acting, no eccentricity, so no trapezoidal variation of soil pressure. Now, to the design, we have already studied the design of slabs, but here the difference is in the slabs we have studied. I think I have told you in the last class also. In the slabs, what we have studied, we are assuming beams on the slabs, and these slabs are supported on the beams, and columns are supporting these beams. Okay, but this one is just another case. This is the slab, this is the column. No beam here. Okay, no beam. This is the directly slab supported. This type of slabs are called flat slabs, and our footing is just reverse of this, just the upside down because you have a bottom slab, then a column support. So this is just upside down of a flat slab or a inverted flat slab. Isolated footing, rectangular isolated footings with uniform thickness can be treated as an isolated flat slab. Okay. So IS 456 provides for design of isolated flat slabs. So here the issue is, since beam is absent, these slabs will not be behaving like the beam, like the slabs which we have designed having the beam, either two-way slab or one-way slab. So we have seen in the design of two-way and one-way slabs, shear is not going to be the criteria. But here in the flat slabs and the inverted flat slab of footing like this, since there is no beam, this column is going to punch the slab. So shear is going to be a criteria. So I have told you we have one-way shear as well as two-way shear. Okay, so that concept will be utilizing when we try to design the slab. So one-way shear is a criteria, two-way shear is another criteria, and of course flexure criteria. And we will be following the provisions of IS 456, where the provisions for flat slab is given. That some locations will be using that also. Okay, so thank you for the time being. So this is the introduction towards isolated footing design. So I have given you two introductions. One is based on the overall idea. Second is on the loading and soil pressure. So please go through this video before doing the problems. Okay. Thank you very much.